So welcome to day 5. Yesterday, continuity told us that when a duct narrows, the flow speeds up. Today's formula, Bernoulli's equation, so answers the natural follow-up question. What happens to the pressure when that happens? This is genuinely one of the most important formulas in this entire series. So because it's the core explanation for how a wing generates lift. So air moving faster over the curved top surface has lower pressure than the slower air underneath. And that pressure difference is lift. So it's also literally the same physics behind airspeed indicators, venturi tubes, and carburetors. So let's begin. Here is Bernoulli's equation, P plus 1 half rho V squared plus rho GH equals a constant. So between 2 points along the same streamline, P1 plus 1 half rho V1 squared plus rho GH 1 equals V2 plus 1 half rho V2 squared plus rho GH 2. See, three terms, each with a physical meaning, right? So P is the static pressure. P is the static pressure, the ordinary pressure of the fluid itself. So 1 half rho V squared is the dynamic pressure, pressure that comes from the fluid's motion. So essentially, it's kinetic energy packed into each cubic meter. And rho GH is the hydrostatic term, so pressure from height, exactly like water pressure in increasing with the depth. So rho is density, assumed constant for incompressible flow. So V is velocity, and is H is height at that point. So this whole equation is really just a conservation of energy. So written in terms of pressure instead of joules. So here is a simplification that makes this practical. For air flowing through a horizontal duct or over a wing, where the height change is tiny. So the rho GH terms are essentially equal on both sides and cancel out completely. So that leaves us with P1 plus 1 half rho V1 squared equals P2 plus 1 half rho V2 squared. So this is the version you will use in almost every problem in this series. So read it like this: a static pressure plus dynamic pressure static pressure plus dynamic pressure, call it total pressure, stays the same at every point along the flow. So if velocity goes up at some point, the static pressure absolutely must go down to compensate. So they trade off against each other. So and this connects directly to yesterday. We already showed that using a duct increases velocity. So Bernoulli now tells us that wherever velocity increase, pressure must have dropped. Today, we will calculate exactly how much. Right. So let's reuse both of yesterday's examples, the wind tunnel and the venturi tube, and finish the job by finding the pressure at the narrow section. So wind tunnel pressure drop. Okay, so example 1, in yesterday's wind tunnel, air entered 10 meters per second. 10 meters per second, air entered at 10 meters per second and accelerated to 40 meters per second in the test section. So assume sea level air density, so 1.225 kilograms per cubic meter, and atmospheric inlet pressure, so 101,325 pascals. So find the pressure in the test section. So step 1, write a horizontal Bernoulli formula. So P1 plus 1 half rho V1 squared equals P2 plus 1 half rho V2 squared. So step 2, rearrange for P2. P2 equals P1 plus 1 half rho times V1 squared minus V2 squared. So step 3, compute the velocity term. V1 squared is 10 squared, which is 100. V2 squared is 40 squared, which is 1600. The difference 100 minus 1600 is negative, so 1500. So step 4, multiply by 1 half rho. 1 half times 1.225 times negative 1500 equals approximately negative 918.75 pascals. So step 5, add to P1 101,325 minus 918.75 equals approximately 100,406 pascals. So the pressure drops by about 919 pascals in the test section. So small in percentage terms. So, but it's a direct measurable result of the air speeding up. So example 2, Venturi tube pressure drop. So yesterday's Venturi tube accelerated air from 30 meters per second to 75 meters per second. So same density and inlet pressure, find the throat pressure. So first, step 2, rearranged formula, same as before. P2 equals P1 plus 1 half rho times V1 squared minus V2 squared. So V1 squared is 900, V2 squared is 5,625. So the difference is negative 4,725. 1 half times 1.225 times negative. So 4,725 equals approximately negative 2,894 pascals. So add to P1 101,325 minus 2,894 equals approximately 98,431 pascals. So that's a noticeably bigger pressure drop than the wind tunnel example. So because the velocity change was bigger. This pressure drop is exactly what a carburetor uses to drop fuel into the airstream. So, and what old mechanical airspeed indicators measured to infer speed. So before recap, 3 mistakes to avoid. First, only drop the row GH cams when height genuinely doesn't change. So like a horizontal duct or level flight. So for climbing or descending flow, you must keep them in. So second, always square the velocities before subtracting, not the other way around. V1 squared minus V2 squared is not the same as V1 minus V2 squared. So third, the sanity check, wherever velocity is higher, pressure must be lower. So if you calculated the pressure went up alongside velocity, you made a sign error somewhere. Go back and check. So now let's recap. P plus 1/2 rho B squared plus rho GH equals a constant. So that's the conservation of energy along a streamline. So for horizontal incompressible flow, so it simplifies to P1 plus 1/2 rho B1 squared equals P2 plus 1/2 rho B2 squared. So faster flow means lower pressure. So your practice question using yesterday's practice that where velocity went from 8 meters per second to 32 meters per second. So find the pressure drop starting from P1 equals 101,325 pascals. Drop your answers in the comments. That's Bernoulli's equation done. So arguably the single most important formula for understanding lift. So tomorrow, day 6, we generalize this even further with the Euler's equation, the differential form that Bernoulli is actually derived from. See you then.